Welcome to this recording on Finite Geometric Series for Unit 1, Chapter 1, Mathematics 2200. We'll be using and developing a formula for the sum of a finite geometric series. A geometric series is the sum of the terms of a geometric sequence, so here are some examples. Now all of these are infinite, they're not finite, but our focus from here on will be on finite series. I present first what the formula actually is rather than proving it right away. The sum of the first n terms is equal to the first term outside of the common ratio exponent the number of terms you have, subtract 1, and that subtract 1 is not in the exponent, all over the common ratio, subtract 1. A reminder of two other relationships from sequences. We'll need those. So in our first one, we do get a common ratio of 0.5, and we can proceed with our formula. Term 1 is 12. Our value we just found, n equals 10. So we find s sub 10 equals 12 outside of decimal 5, exponent 10 minus 1, all over decimal 5 minus 1. Doing that calculation with our calculators gives me 23.9765625. Make a long story short, that's 3069 over 128. The next one has no common ratio. It actually has a common difference. Therefore, it's an arithmetic series. I threw that one there to remind you of the importance of checking the type of series you have. You can do it using this formula. For this next one, working on the common ratio, 1/16 divided by 1 over 64. That's equal to 1/16 times 64 over 1. Dividing the 16 into the 64 goes 4 times, so I've got a ratio of 4 there. For the next pair, 1/4 divided by 1/16 becomes 1/4 times 16 over 1. 4 goes in 16 4 times, so I have a ratio of 4 again. And the last available pair that I have is 1 divided by 1/4, so it's 1 times 4 over 1, which is 4. So we know our R value is 4. Now we want to use our formula for the sum of the terms, but we still don't know n. But guess what? Our related sequence formula is here to bail us out of a pickle. We can use that to find the number of terms. The last term we know is 1024. Term 1 is 1 over 64. R is 4. So I bring that 64 over, multiply it by the 1024, and I get 65,536 equals 4 exponent n minus 1. A little guess and check with our calculator shows that 65,536 is 4 exponent 8. So we've got 4 exponent 8 equals 4 to the n minus 1. N must be 9. We just cross off those bases, make the exponents equal, and we get 9 equals n. We now have everything needed for our series formula. We figured out that n is 9. So substitute everything in. We're finding the sum of the first 9 terms. Term 1 is 1 over 64. Outside of 4, n is 9. And we have r minus 1, that's 4 minus 1 in the bottom. So inside the brackets here we have 262,143. That's all over 3. And this 3 divides into 262,143, 87,381 times. So we've got 87,381 all over 64 for our final answer. We finish with a proof of the formula. A geometric series can be expressed as term 1 plus term 1 times a common ratio. That'll give us term 2. Then term 3 will be term 1 times the common ratio twice, so it's r squared, etc. Until we get out to the last term, the nth term is t1 times r to the n minus 1. I've also included the term previous to that. Our second step is to take all of that and multiply it by r. So in other words, I multiply the left side here by r, and then every single term gets multiplied by another r. Like so. Let's see what that does. That means r times s sub n is equal to term 1 times r. Then we get an r squared here for the next term, plus T1r cubed for the next one. So all the exponents on the r's are going up by 1 from what they were before. So by the time we get to this term here, the total exponent now will be r to the n minus 1. Think of it like this. We're adding the exponents. Bases are the same, add the exponents. And therefore, our last term becomes r to the n. Our next step is to take that expression and subtract the original one. So r times s sub n equals this whole line here. We're subtracting the original expression. So I'll put big brackets around all this. And now, because I've lined up my like terms, it's easier to see T1 times r subtract T1 times r. They're going to cancel. These two are going to cancel. These two are going to cancel. And these two are going to cancel. So r times s sub n subtract s sub n is equal to, well, this is going to be a negative here, and this is going to be a positive. So I got term 1 times r to the n minus term 1, because the term 1 becomes negative due to the subtraction. Our next step is to remove common factors on both sides. So on the left side, I will have a common factor of s sub n outside of r minus 1. On the right-hand side, I've got a common factor of term 1 outside of r to the n minus 1. Starting to look familiar? All I need to do is bring that r minus 1 over to the other side and divide it. So I've got term 1 outside of r to the n minus 1 all over r minus 1. Key ideas. Here's the formula for the sum of a finite number of terms in a geometric series. Sometimes you got to use these relationships to get information needed to use that formula.